Welcome to The Explainer. Today, we're diving into what I like to consider a masterclass on one of the absolute most critical, yet honestly frequently underestimated engineering challenges of our modern era, and that is sustainable materials selection. Look, every product you see, touch, or use begins with a fundamental choice of materials. But as our global industrial footprint just keeps expanding, we literally can no longer afford to select materials based purely on what's cheapest or what's right in front of us. We have to look at the entire picture. So today, we're going to explore the rigorous framework that top-tier engineers and designers use to make choices that are both technically sound and environmentally responsible. Here is our syllabus for today's session. We'll start with a quick introduction to material selection, then dive right into understanding life cycle analysis. From there, we'll trace the material journey, assess the environmental impacts, look at the very real benefits of pollution prevention, and wrap up with applied prevention strategies. Let's get into it. Section 1. Introduction to material selection. Finding that crucial balance between our engineering needs and our ecological responsibility. Moving right along to Section 2, Understanding Life Cycle Analysis, which is basically our standardized diagnostic tool. So, what exactly is life cycle analysis, or LCA? Well, it's a vast evaluation that gives us a crystal clear idea of how the processes involved in a product's manufacture, its day-to-day functioning, and its ultimate disposal affect the environment. Notice the timeline embedded in that definition. This analysis absolutely must encompass the entire lifespan of the product. We aren't just looking at what happens on the factory floor. We're evaluating the total ecological toll from the exact moment its raw materials are pulled from the earth all the way to the moment it's finally discarded. Section 3. The material journey. Let's break down this chronological life cycle. Every material takes a cradle-to-grave journey. You can think of it kind of like a product's passport, getting a new stamp at every major phase. Step 1 is resource acquisition. Step 2 involves the manufacturing processes. Step 3 is transportation. Step 4 is the actual performance of the material when it's being used. And Step 5 covers the end-of-use options. As we walk through these 5 phases together, I want you to keep in mind that each specific step presents its very own unique set of environmental and economic challenges. Let's start at the very beginning with resource acquisition. I want you to really think critically about the origins of our materials by asking a couple of vital questions. First off, how is the material collected? Are we mining it, harvesting it, synthesizing it in a lab? And second, how much of our natural resources are utilized in this very first step? You see, the environmental debt of a product begins accumulating the exact second we extract its raw materials from the planet. Now, once we have those raw materials, we have to process them. And here's a fascinating engineering reality for you. Material requirements can drastically differ for the exact same end product, depending entirely on the manufacturing process you choose. If you go with a highly inefficient manufacturing process, you're going to require vastly more raw material to yield the exact same output as a highly efficient process. So the engineering choices made during this processing phase directly dictate the overall volume of resource consumption. Next up in our journey is logistics, specifically transportation. Ask yourself, is a material locally available? And is it actually cost-effective to move it to the manufacturing site? This is where global supply chains get incredibly complicated. You might find a material that's super eco-friendly to harvest and process, but if it has to be shipped on heavy-duty freighters across 3 oceans just to reach your factory, well, those massive transportation emissions completely negate the initial benefits. Just to put that into perspective, maritime shipping accounts for nearly 3% of global greenhouse gas emissions. Moving heavy materials changes the entire equation. Phase 4 is performance. And let's be real here, sustainable choices still have to meet rigorous, real-world standards. The chosen material absolutely must deliver superior performance as part of the product when we factor in the business and economic aspects. We simply cannot sacrifice functionality. Think about it. A biodegradable car engine part is completely useless if it melts at high operating temperatures, right? Sustainable material selection means finding that perfect intersection of high structural integrity, economic viability, and environmental responsibility. And finally, we reach the end of the line. End of use. When a product reaches the end of its life, how is it treated? Is it getting reused? Is it recycled? Or does it strictly need to be disposed of with extreme care? A product's ultimate fate isn't just some accident. It is a deliberate engineering choice made way back during the design phase. If a product ends up sitting in a landfill, leaching chemicals for a century, that is fundamentally a failure of initial design. Section 4. Assessing environmental impacts. Let's look at the measurable consequences of this journey. We measure environmental impact through several primary metrics: greenhouse gas, or GHG emissions, total carbon footprint, and the degradation of land, water, and air. Now, this isn't just an abstract list of buzzwords. These are hard, measurable data points that we must consider in detail when utilizing any product. Every single kilojoule of energy used and every liter of wastewater produced during manufacturing contributes directly to these impact categories. Section 5. Benefits of pollution prevention. Let's pivot to the tangible upside. Let's be clear, sustainability is just good business. On the economic side of things, you're looking at reduced costs for cleanups, much lower disposal costs, and overall lower emissions. And then from a compliance and social standpoint, you gain a significantly easier time complying with regulations, lower risk from toxic effluents, and vastly higher social acceptance. Proactive pollution prevention yields massive returns, delivering those vital socio-environmental gains right alongside high economic profitability. Section 6. Applied prevention strategies. How do we actually do this? So how do we pull this off in the real world? Well, these prevention methods form a web of interconnected engineering strategies. First and foremost, you've got to incorporate environmental considerations straight into the design itself. Solve the problem before it even exists. From there, we actively look for ways to reuse materials, especially taking waste from entirely different industries. We can also dramatically improve our outcomes just by educating personnel on better work practices and ensuring stringent safety standards are in place to prevent spills. Plus, utilizing waste-to-energy methods and consciously choosing alternate, lower-impact materials are incredibly effective tactics. Proactive design is the key to solving those end-of-use problems we talked about earlier. Which brings us to our final takeaway. Sustainable material selection absolutely is not just some environmental obligation, it is a comprehensive design and economic strategy. Every material choice you make echoes through that product's entire life cycle. By actually applying the frameworks of life cycle analysis and proactive pollution prevention, we stop treating environmental impact as a mere afterthought, and we start treating it as a core metric of engineering excellence. So the next time you hold a manufactured product in your hands, don't just ask what it does. Ask yourself, what ecosystem had to be altered to put this in my hand, and where is this going to be 1,000 years from now? Thank you so much for joining me for this explainer, and keep learning.